So today we are going to talk about parameters of operation amplifier. We have completed modes of OPAMP, and before modes of OPAMP, we have discussed what is an OPAMP or definition and bit detail of that. Now, what do you mean by parameters? Parameter is something that will tell you the characteristics. And there are different op-amps and they have got different characteristics. So if you know the characteristics of different amplifiers, when you have to make a circuit, you will be easily able to choose which one among the available op-amps have characteristic matching with what you are looking for. That is why these characteristics or parameters are very important, and we are going to discuss that. So one of the important thing is CMMR. That sounds like a complicated word, but it is very simple and important for us to know this for any available op-amp. So what do we mean by CMMR? It stands for common mode rejection ratio, and what it is defined as the ability of an op-amp to reject common mode input signals is called as CMRR, and it is represented as a mathematical equation which is equal to A open loop divided by A common mode gain. We will discuss this in future, and generally since this value is very higher, we use decibel value, and decibel value to represent this one is CMRR dV is equals to 20 log the value of AOL divided by ACM. It sounds a bit complicated, but why rejection ratio is very important. Generally, our op-amp are used in electronic circuits, and one of the challenge of electronic circuits is in the input you have got signals and noise both. You need signal, but you don't want a noise, right? So to suppress this, we use an amplifier having good value of CMRR. Fine. op-amp having good CMRR will be able to reject noise in a good way, right? So that is why this number is important. And whenever you are going to buy an op-amp, for example, you will ask, or if you read the specification of that op-amp, you will check for the CMRR, and the one which is good for your requirement, you will choose that. So you got my point. For example, if you are going to buy a weighing machine, car, for example, what you are looking for? What is the engine capacity liters? It is 1.6 to 2.5 or something. Similarly, you will look for its power, how much horsepower and all. So similarly, one of the important parameters of op-amp is having good value of CMRR, right? And generally, you will get a question in the exam. You will be having the values of A open loop and A common gain, and you have to find out CMRR, most of the time decibel. Okay, I have got a question from a guy that I have said that common mode will give us zero. Very good. Yes, a very good question from your friend. We expect this to be zero, right? An ideal op-amp will give you zero, but practically it gives some value. Closer to zero is better, but when we are going to buy a op-amp, every time your budget is not very high, right? So it depends on what kind. For example, if you're designing a circuit which is for audio communication, you may be a bit flexible. Why? Because our ear is not very sensitive. Some imperfection it will accept, but when you are designing something for video signals, our eyes are very sensitive if you compare this with the ear, right? So in that case, even a small value of common gain will not be acceptable. You got my point, yeah, Muhammad Salman? What I'm telling is it should be zero. I mean, if, for example, your class is at 10, you should be at 10, right? But sometimes you are delayed by 1 minute, 2 minutes, and sometimes you come some real problem. You may be late by 10 minutes. So these are the same with the practical devices. We expect it to be zero, but we never get exactly zero. Otherwise, or it is very expensive, and most of the time we may not afford, depending on the circuit we are going to design. You will understand this in future, but for time being, you understand that CMRR is a value that tells the quality of OPAMP you are having. Fine. Jazakallah khair. A very good question. Now, voltage and current parameters. As we are talking about different parameters, the first parameter was CMRR. The second parameter is input offset voltage. By input offset voltage, what we mean is it is the differential DC voltage required between the inputs to force the output to 0 volt. Now, what do we mean by this? If you know weighing machine, or you say mizan, if you know weighing machine, what we expect, whatever thing we'll put, it will tell the accurate value. But if you will notice carefully, most of the weighing machine has a knob to set it to 0. For example, you are weighing something in a bucket. The bucket itself is having some value. So what you want, after putting bucket, if its value is 0, then your weight will be perfect. Similarly, we want to apply something in the input and get something in the output. But if there is something already present in the output, then after applying input, your output will not be very perfect. So what we want, to apply some input DC voltage in such a way that your output is 0. Then we apply our actual input so that our output will be perfect. So this voltage that you apply in the input is called as input offset voltage. Is it making sense? If you understand the behavior of weighing machine in a good way, it will be more clear that input offset voltage is a voltage that we apply in the input of OPAMP, and the purpose is to make the output of OPAMP as 0. This is a precondition which is needed to make sure that once your output is 0, after that, if you are applying your input signal, you are getting a perfect output. Okay. Anyway, we will go through this in detail so that you will find it more understandable. For right now, that is all we can say for this point. Now, again, in what is input bias current, I'm reading whatever is there on the screen. Input bias current is the average of two DC currents required to bias the differential amplifier. The average of two DC currents. You know, there are two terminals, inverting, non-inverting. If you assume them as 1 and 2, then what will be the value of this one? Current first plus current second divided by 2. That is average. Now, input offset current is the difference of the two currents. You have got two input terminals and you will get two currents. The difference is called as input offset current. Okay. Differential input impedance. Now, what do you mean by differential input impedance is the resistance between the inputs. Your device is having two parts, input and output. So, differential input impedance is the value of input impedance, and common mode input impedance is the resistance between each input and ground. Generally, in case of op-amps, we apply two signals, right? So the impedance with respect to the ground is called as common mode input impedance. How you will calculate? You will connect one terminal to one input, and another terminal will be grounded. The value of impedance you will get will be called as common mode input impedance. And output impedance, as the name suggests, the value of resistance you will measure at the output will be called as output impedance. And another important parameter is called as slew rate, and this is the last but not the least parameter, which is called slew rate. Now, if I'm reading this, the slew rate is the maximum rate of change of the voltage signal in response to a step input voltage. Now you know how a step signal looks. In signal system, most of the time you have read a step signal, and how it looks like this. At this when time t equal to 0, on the left side its value is 0, but on the right side its value is 1. So why this signal we consider in the input? This signal has got highest frequency change. So if you apply this signal to the input of your op-amp, how your op-amp is responding to this signal, it will give you a good picture of how sensitive your op-amp is for fast signals or high frequency signals. It sounds a bit confusing, but I'm going through this in detail. Again, it is good to read it again because it is an important topic, and always you are going to get some questions from this. The slew rate is the maximum rate of change of the output signal in response to step input. Now I'm giving you a real scenario. You have got an op-amp, right? Now there are two different types of signals you are applying at different time. And the first time your signal was up to frequency 1 kilohertz. This color looks very light. I will change the color. In the first time frame, you applied a signal whose frequency range was up to 1 kilohertz. What it means is that your signals frequencies will go up to 1 kilohertz. Now, for the same op-amp, after some time, if you are applying an input signal whose frequency will go up to 1 megahertz, then of course the op-amp that you are having is not going to be having the same way for these two signals, right? You are getting my point? For the input signal applied, if frequency variation is huge, your op-amp will behave in a different way. So how sensitive your op-amp is regarding high frequency signals, that is represented by this value, that is slew rate. And higher the value, it means for faster variation in input signals, you are getting reasonable output. But anyway, as we will get in detail, the picture will be more clear. But for timing, that is what I can say regarding slew rate.